In the last video, we did some analysis on horizontal circular motion, and now in this part we'll look at vertical circular motion under the influence of gravity. So here's a vertical circle with a mass m at an angle phi from the vertical in the downward direction. So let's think of this as being a mass on a spring and it's spinning around. And potential energy and kinetic energy are basically interchanging between those two forms. Free body force diagram on M, we have the mass, and in this direction we have radial. I mean, either toward the circle or toward the center or away from the center is the radial direction. And then from the vertical, we have angle phi, alternate interior angles. Both of these angles are phi. So here's the tension. There's a tension in the string that's holding the mass M. All right? Now that's a real force acting on M. But there's another real force acting on M, which is mg, the weight. So these two forces are the only real forces acting on this mass. Now the part of the weight that's acting radially is the part of this force that's in the direction radial. And of course, if you take a perpendicular, where the perpendicular to this radial line intersects the tip of mg, that's the amount that's acting radial, and it's outward. By the same token, the amount that's acting tangential is mg sine of theta, so that's this much. So these two components account for the weight in the radial and tangential directions. So we cross out mg. Now let's look at the tangential and radial accelerations from this force. In the tangential direction, we have that the parallel force, tangential parallel, is m a parallel, which is mg sine of phi. And that's it. There's nothing else. In the radial direction, we have two forces. We have tension acting inward, mg cosine of theta acting outward. They're acting in opposite directions, so the sum of the forces, which by definition is centripetal force, is tension minus mg cosine of phi, which is mv squared over r, definition of centripetal force. And therefore, we have solved for the tension in the string at any arbitrary angle theta as such. Tension is mv squared over r plus mg cosine of phi. Let's consider some other positions on the vertical circle under the influence of gravity where it's interesting and useful to think about what the tension is. So, at the bottom. Well, at the bottom, the tension is the greatest because the tension has two jobs. It has to hold up the weight of the mass, plus provide all the centripetal force to cause it to go on a vertical circle, actually just a circle, all right? And so it's mv squared over r. There's all the centripetal force, plus it has to hold up the weight. So mv squared over r plus mg. At the top, gravity is helping, all right? So gravity is acting inward, which is down, and that's helping the centripetal force. So the tension is less. The tension has to just do what gravity can't. And so it's the centripetal force, the total amount required, minus gravity, because gravity is already helping, reducing the tension that's needed. At the sides, 90 degrees or 270. If you think about it, at those locations, the tangential force is gravity. So gravity is not contributing to the tension plus or minus because it's perpendicular to it. Therefore, it's just mv squared over r. And finally, the difference between the tension at the bottom and the tension at the top is obviously mg minus negative mg, which is twice the weight. So now we're ready to consider the physics of a roller coaster. In this case, we'll analyze the situation where the vertical motion is too fast, quote unquote, meaning that it's going fast enough that at the top of the loop, gravity is insufficient to provide the centripetal force to cause it to execute the curved motion that it's undergoing. Here comes the anti-gravity train up to the top of the loop. So what I meant by that, of course, was that at the top of the loop, you're going fast enough that you don't fall out of the loop. Namely, gravity that acts down is insufficient to provide all the centripetal force needed to enable the train, the car, and the passengers therein to execute that curved motion. So the magnitude of the velocity, the speed, is not constant because, you know, gravity is acting tangentially as well. Notice the teardrop shape. The teardrop shape of this actual, you know, roller coaster ride is designed that way because you want to make sure that the curvature at the top where you're going slower is sufficiently small so that you do need more than gravity to execute the loop. Otherwise, gravity will pull you out of the loop. But then at the bottom, notice the radius is much larger. You want to make sure of that so you don't black out at the bottom. Because basically at the bottom, the forces that you experience as a rider are going to be the support forces, which are going to exceed multiple G's if you're going very fast, and you'll black out. So then you get, you know, lawsuits and national attention, and the rides close down and go out of business, all that kind of crap, you know. All right, anyway. So potential and kinetic energy interchanging with each other again. Now at the top, where we're looking at it right now, the centripetal force is the weight plus the seat force. The weight, of course, acts straight down. The seat force also better be acting downward, pushing on your gluteus maximus in this direction. Because if not, then gravity just may be pulling you right out of the seat. So you got those two forces in the same direction. You just need to make sure that centripetal force is sufficiently large. It needs to be big enough so that you need that seat force. So let's take a look at what this looks like. So here we are at the top. Gravity, seat force. Now the seat force can be any arbitrary size. If you're going just the right speed, it will be just Fg by itself. This will be 0. But F seat might be really long if you're going really, really fast. So it can vary in size to any value, but always points down. Now, the addition of those two is the centripetal force, because centripetal is toward the center, and both of those are toward the center. So you have mg plus f seat is mv squared over r. And so you can solve for the f seat, which is really what you're interested in, being the rider. That's what you experience. And f seat is mv squared over r minus mg. So in like manner, you can analyze other types of seat forces with different types of motion. Now at the bottom, as I already alluded to, you've got a situation where the seat force, the support force, is potentially much greater. So you better not have the as we fall down in elevation. And here we are at the bottom. And at the bottom we have Fg acting down. But now think about the direction of the seat force. Obviously it's pushing up on your rear, and that is like this. Now F seat might be a lot bigger than what I'm showing here. All right, but this is certainly larger than Fg because it's got to overcome gravity and provide the centripetal force needed to go through this arced path, this curved path, and that's an additional upward force. So we have Fc, depending on how fast you're going, and the radius of curvature, so I'm showing it of that size. And if you look at it, it's the sum of the forces. So the sum of the forces is F seat in the direction of the net force, which is Fc. F seat minus Fg in the opposite direction gives you the centripetal force, which is mv squared over r. And so F seat is the centripetal force plus the weight. And because those two are added together, and this is what you feel, this could be very large. Notice mg is what it is. That's 1g, basically, a force that you feel. And if r is really small, depending on what v is, this number could be very large. So make r relatively large so that this number is relatively small and you don't black out.